All right, so now we want to talk about resistance. So we already understand that current I, measured in amps, is the flow of electrons or the flow of electricity. Number of electrons, or aka charge, right? So delta Q divided by T, or delta T, charge per unit time that flows past. And V stands for voltage or electrical potential difference in these equations here. So V, voltage, electrical potential difference, aka EMF or electromotive force, how hard you're trying to push these electrons around. So I have something pushing electrons, and then I have a measurement of the electrons actually flowing, and the harder I push, greater voltage, the higher my current should get, right? That also, though, depends upon how much the object that I'm trying to push the electrons or the current through resists. That's this idea of resistance, which is the property of an object that determines how much current can flow through depending on how hard you're pushing, right? You push a little bit harder, aka a greater voltage, you're going to get more current for the most part. We'll get to that here in a second. Resistance is defined as how hard you push, the voltage, divided by the current that is actually able to be induced or to flow through it. So that's going to be the resistance. Units is in ohms, and that's a Greek letter omega, like that. If you will, a horseshoe with 2 feet poking out, if you need to kind of think about that in a little bit more English idea there. Now, from this equation, this idea of resistance, we get this equation, V equals IR. Now, this is lots of times talked about as Ohm's Law, even though Ohm's Law isn't necessarily that equation, but it's kind of the crucial equation behind what we're doing here. Voltage equals current times resistance there. So if I know my voltage, I know my current, I can calculate resistance, or any thereof. If I know 2 of the variables, I can calculate the third. Another equation for resistance, if I don't know the voltage, I don't know the current, instead I just know about the properties of the thing that I'm going to try to push the current through. I just know about the object. I haven't actually plugged it into a circuit yet. I know physical attributes of it. For example, I know the physical attribute of length of a wire and area, cross-sectional area of a wire, and then I know what it's made of. Rho stands for the resistivity of a material. All right, in other words, for this type of material, how hard do the atoms try to hold on to the electrons, prevent them from being able to flow? The resistivity is a measure based upon that, and it's per each individual type of material, and it's different for every type of material. So if I know the type of atom, the length of the wire, and then the cross-sectional area, I can calculate the resistance. Now you might wonder, what do I mean by cross-sectional area? That is a term that's going to come up quite a bit in physics and in math, being able to do with cross-sections of it. Quite simply, if you were to think about it, imagine taking scissors to a wire and cutting it, and then looking at one of the ends. Whenever you look at one of the ends that you just cut, the area of that two-dimensional shape, that's the cross-sectional area. If I were to draw it out a little bit better, imagine here is my wire, and then I cut it. If it's a wire and it's a perfect cylinder, whenever I cut it, I will have a cross-sectional area of a circle there. So I bring this, if you will, circle as my cross-sectional area. So the area here is going to be area of a circle, pi r squared, right? And if you know r or the diameter, you're good to go. So there's 2 ways you can actually calculate resistance, either using, we'll call it Ohm's Law, even though it's not, V equals IR, kind of the main base equation, voltage equals current times resistance. Know 2 of the 3, substitute in, right, plug, chug, get the third. Or if you know about the material itself, like the resistivity, aka what material it is, you look up what the resistivity of, let's say, here there's copper, right? So if it's a copper wire, I look it up in a book or a table, know the resistivity. Length of a wire and the cross-sectional area of the wire, I can calculate its resistance just from its properties. Now, Ohm's Law actually states the current through an object is directly proportional to the electrical potential, and that should say electrical potential difference applied to it. In other words, as I increase my voltage, right, my voltage goes up, my current goes up in a proportional manner, meaning I should have a linear graph. For every extra volt I apply, you know, if I go from 1 to 2, I get an extra proportional to let's say 4, right? I get an extra proportional increase in my current there, a linear graph. That's Ohm's law. Now, not everything is ohmic, meaning that it follows Ohm's law. Some things don't. This would be an idea of a very nice resistor there that perfectly follows Ohm's law. This would be a graph of maybe a filament lamp, aka a regular incandescent light bulb, the thing that actually was just outlawed by the government here recently in 2014. That are all being phased out now, that has a little filament that glows white hot inside of it. A filament light bulb has a portion that follows Ohm's law very nicely. In fact, the portion between those two lines is pretty much a straight line. It's very ohmic. But then as it heats up, we start meeting kind of the limits of this material, if you will. And as you apply extra potential difference, extra voltage, notice you don't get as much return for your current. Instead, it starts fading off. So just because you go from, I don't know, let's say this is 4 to 8, you double your potential difference, doesn't mean that you're going to end up doubling your current. Maybe over here, this is, let's say 2, and then up here, right? Let's see here. Yeah, something like that right there. That's only 3, so it doesn't double there. You start getting limited returns. You're pushing too hard and the current can't keep up. So this would be an example of something that is non-ohmic, and this would be something that is ohmic. You push, you double the voltage, you get double the current. That's going to give you an ohmic material. You double the voltage, and you don't get double. You get something less on the current. Now, there are a lot of other things, diodes and capacitors and all these other things that actually have very wacky looking graphs here that aren't ohmic as well. The definition of ohmic, though, is a nice linear line, directly proportional, electrical potential, aka voltage, and current. Now, I also need to point out that the slope of something that is ohmic over here, the slope of the line has meaning. Using our equation of V equals IR and then solving for what I, rise, that's the current, right, because I have my current on my y-axis, over run, voltage on the y-axis. Whenever I solve that through, I'm going to see that 1 over R is going to be my rise, delta I, over my run, delta V. So I'm expecting the slope of this line in anything that is ohmic, that has current on the y and voltage on the x, to be 1 over the resistance of that item. And that slope remains constant. Notice it's a line there, it does not change, so the resistance must remain constant. On the other hand, whenever you push harder, you put in more potential difference, and you get less current out, that means your resistance is changing. Notice the slope is changing here, right? 1 over R means that R is actually getting greater whenever you're pushing harder and getting less current out. Likewise, if these axes were reversed, which normally does not happen, but you have current on the x and electrical potential difference on the y, I would expect my slope to just come out to be the resistance, not instead of 1 over the resistance. But this is the way the graph normally is. You would expect your slope to come out to be 1 over R. All right, 3 questions I want to solve here for you. The first one, what is the resistance of a 5-meter long copper wire with a diameter of, that says 5.4 millimeters there? Since I know about the details of the wire, nothing about a voltage or a current being applied to it, I need to use the equation resistance equals resistivity, rho, times the length of the wire divided by the area. Now, whenever I do that, it becomes a very plug-chug style problem with one thought. You have to know how to get the cross-sectional area here. So I'm looking for R. The resistivity of copper, you'll look up in a table like just a few moments ago in this video. You see that copper has a resistivity of 1.7 times 10 to the 8th. This is a 5.0 meter long copper wire divided by the cross-sectional area. Now, most wires come as cylinders, right? 3-dimensional shape of cylinder, and whenever you cut it, you get a cross-sectional two-dimensional object of a circle. So the area of a circle is pi r squared. Now, I'm not told the radius, but I am told the diameter. Now, the diameter is 5.4 millimeters. To get the radius, I have to divide by 2, and milli means times 10 to the negative 3, so 5.2 times 10 to the negative 3, all divided by 2 here. That's going to be my radius squared there in the denominator. And now I just substitute into my calculator, and I get my resistance. And I come out with a resistance of 0.011 ohms, which is the idea behind wires. This is why copper wires are so good. You should have a very low resistance in your wire to where it can pretty much be neglected compared to everything else in the circuit, which are lots of times in kilo ohms, for example. Remember, here's my area, here's the resistivity, entire area, pi. This was the radius squared. Here's the length. All right, so next problem that we're going to solve now. What is the resistance of a toaster that has 120 volts applied to it and allows 85 milliamps to flow through it? Since I know about the voltage and the current here, I'm going to use V equals IR. So the voltage, 120, equals my current, 85 milliamps. Remember, milli means times 10 to the negative 3. And I'm just going to go ahead and put that in there and let my calculator take care of the scientific notation, times R, what I'm looking for. And so now R is just going to equal dividing over 120 divided by 85 times 10 to the negative 3, and you shove that in. I come out with 1,400 ohms. If I was to translate that into kilo ohms, that would be 1.4 kilo ohms here. Next question, when 240 volts is applied, it allows 160 milliamps to flow through it. Now, is this toaster actually ohmic? Is the question. In between that range that was just given, is this toaster ohmic? So once again, I'm going to use V equals IR because I know about the voltage and the current here. My voltage is now 240. My current is 160 times 10 to the negative 3. I'm going to solve for R, divide both sides by 160 times 10 to the negative 3. And you can see here that as I increased my voltage, or my electrical potential difference, as I pushed harder, I actually got less current. I actually doubled the voltage and did not get double the current, meaning that the resistance went up. For something to be ohmic, the resistance must stay constant here. So this is a non-ohmic device. As you push harder, you get less return.